two of the main theorems stated even before I opened my mouth, but he didn't read it properly. So the second one is that nowadays is mandatory that we show that we are environmentally responsible and that we fight fake news. So if anyone tells you that trees are not real, you're going to say, I went to a conference and I saw the proof. So the proof is here. Hopefully I'm going to get. And third, so in this business that I'm going to present here, we're suggesting here the use of some combinatorial tool that we are naming Q factorization graphs. And especially as a tool for being able to express results in a simple way. So the fact that we can state two of the three main results that I want to talk about in 2 lines should be some sort of statement of that the machinery is good in order for you to keep track of the things. But before I begin, so we always start thanking the organizer for the opportunity of speaking here, but I think this time I cannot do that because I have to give a special, different kind of thanks. And earlier this year, Slava sent me an email. What happens? You're not registered. Well, I'm not. I don't think I should be giving a talk this time, so I didn't register. Well, anyways, so he completely ignored my concerns, and 2 months later, here's the schedule. You're giving a talk. So I wanted to thank Slava for not allowing me to run away from the pressure of preparing something for giving it. Yeah, I couldn't escape. So the practical outcome of that is that it forced me to stop postponing making public these results that I'm postponing for more than a year already. So this is jointly, it's part of the project of my PhD student, Clayton Cristiano da Silva. And also the reason I was postponing is that, although I'm going to show that, let me use this, that trees are real, but differently than totally ordered graphs, they are not always prime. And one of our early goals was to prove that, to describe precisely which trees are prime and which trees are not. And we never reached that point, and I kept postponing. Let's not put the things out before we reach that. And I find maybe enough is enough. So since Monday, there are 2 papers on the archive telling the story that I'm going to tell you here today. And hopefully the colleagues that work on this kind of things will help us describe precisely which trees are prime or not. So thank you, Slava, not for the opportunity, but for not allowing me to escape to give this talk. So, all right, so I have to start by telling you what the context is. And so in the last 6 months BC, I gave a couple of talks about these preliminary stages of this story, including the lead jar in Chengdu, which I do not know if it's BC or AC. If you know, C is for COVID-19 and Chengdu was 2020, right? But so if you were either in Chengdu or an even earlier version of this talk in Rio in July 2019, so these first 2 slides are going to be exactly the same, which is the context of the story here. But hopefully I'm going to end the talk proving that trees are real. Okay, so to start explaining the context, let me start from a much broader setup than the one I'm going to work with in the end. So the problem can be posed, the main question may be posed for a much broader context, namely you start with any monoidal category. So that's a category which has a notion of tensor product and unit object. And then you define the notion of a prime object in the category. So as you can expect, a prime object is going to be some object that the only way that you can express it as a tensor product of other 2 objects is if at least one of them is the unit object. Okay? So since I come from lead theoretical representation theory background, so let's start with the context that all of us study early on in the game, which is the category of finite dimensional representations for a finite dimensional simple algebra, on which category the answer is absolutely trivial. And the answer is every simple module is prime. Why? Well, because, so from the definition, the way I wrote the definition, 1 is prime. If you don't like that 1 is prime, you just change it. But if I keep 1 being prime, then the trivial representation is prime. Okay? And except for the trivial representation, if you tensor any other 2 simple modules, the result is going to be something which is reducible. So a simple module cannot be expressed other than the trivial representation, cannot be expressed as a tensor product of other 2 things. Well, okay, so, but the definition in principle of prime modules does not need to be simple, but if you don't restrict yourselves to the class of simple modules, then there are sort of useless things that you can do to produce prime representations. You just take any representation of prime dimension, like you just add a prime number of times the trivial representation, and you get a prime module. That's boring, right? So what we are trying to answer is, in the class of simple modules, which one of them are prime? And in the most classical setting, it's very easy, everybody is. So now, so suppose that your category is not only monoidal, but also abelian and has some finiteness assumption in it, which in my case is going to be that the modules are finite dimensional vector space. So in each case, obvious induction argument will show that every simple module can be expressed as a tensor product of simple prime modules, okay? So the talk is to try to answer, or not to answer because this is a very difficult question, but to make some progress towards answering this question of classifying the simple modules which are prime in the category of finite dimensional representation theory of quantum affine algebras. I'm glad Nicolas is here, so maybe he knows of other Hopf algebras on which a category has interesting, so for instance, the category of finite dimensional representation of finite dimensional Lie algebras, the question makes sense, but the answer is boring. Here, the answer is certainly interesting and relevant because this is all motivated with connection with mathematical physics and it has strong combinatorial flavors, and so there is a lot of connection with many things. So maybe there are other Hopf algebras with categories on which the question is also having an interesting and relevant answer. Yes?
I think I don't understand the notion of prime. Is I really the unity object of C, or can it be any invertible object?
No, the object that you tensor and you don't change the isomorphism class of the original model.
But what happens if you have an invertible object in your category? And wouldn't that make the unity not prime? And just take a one-dimensional representation of a Lie algebra, which is not trivial, and tensor a prime one by that.
Okay, so maybe what you're saying is that maybe my definition in the broader context is not well formulated. Right?
I think, yeah,
okay.
So typically you take this thing not to be one, but take a unit.
Okay. So in this category, such phenomenon doesn't occur. We don't have invertible objects in the category I'm going to work on. So what you're saying is that the definition in the broader context is not well defined.
You can have a one-dimensional representation
in the category of quantum affine algebras? No, that's right. That's what I'm saying. In the context I'm working on, it doesn't happen. So what you're saying is that maybe my generalization of the question is not well formulated. Yeah. All right. So before I go to quantum affine, let's move through the classical affine, but it's finite dimensional representation. So it's well known that studying finite dimensional representations of affine Kac-Moody algebra, it's the same thing as studying for the loop algebra, which has already appeared this week in the talk of Rchiki Rocha that was talking about the maps, representations of map superalgebra. So this is the most studied map superalgebra, the loop algebras. It has this bracket that you're seeing there, right? So in particular, one of very natural thing to do is that you have this Lie algebra homomorphism from the loop algebra to to the simple Lie algebra. For any complex number, non-zero complex number you choose, you can evaluate the polynomial part of the thing. So this is called an evaluation map. It's a Lie algebra homomorphism, and then you can pull back the action of G on any module to an action of G tilde. So this is called an evaluation module, so which I'm denoting by D. So this is the G module V with action pulled back by the evaluation map. So in one of the first Charin-Presley papers, they characterized exactly when the tensor product of two evaluation modules over a simple module is again simple. And it happens exactly when the two evaluation parameters are different, right? And moreover, in fact, this can be used to give the classification of the simple modules in the category of finite dimensional representations for the loop algebra. So every simple module is a tensor product of several evaluation modules with distinct parameters up to reorder. In particular, this answers the question for this category. So in the category of finite dimensional representations of modules for the loop algebra, the simple prime modules are exactly the evaluation modules. Okay, so now we have simple modules which are not prime, contrary to the previous example, but it's still very easy to characterize which ones are the prime ones. They are exactly the simple ones, the evaluation ones. So then we want to go with this story to the quantum setting, and then the thing becomes very complicated. And one reason that the things become very complicated is that there is no quantum analog, in general quantum analog of the evaluation map. So the evaluation map exists if the underlying simple Lie algebra is of type A, but even in type A, this theorem here, the second part, the moreover part of this theorem is false except for type A1. So outside SL2, it's false that every module is a tensor product of evaluation ones. Every simple module is tensor product of evaluation ones outside SL2 case. Okay? So this machinery, even for classifying the simple module, is not available anymore. So what you do, you go back to the notion of highest weight. But the notion of highest weight is built up on in this manner here. So if you choose a triangular decomposition for the underlying finite dimensional Lie algebra G, and then you consider the loop algebra over each of the three parts of the triangular decomposition. So this admits an analog for the Drinfeld-Jimbo quantum group as well. So it has a quantum analog of the triangular decomposition if you consider the loop over each summand of the triangular decomposition. And in particular, the loop algebra, the quantum loop algebra over the Cartan part is an abelian algebra. So you're going to define the notion of weights as eigenvalues of the action of this abelian subalgebra. And, well, highest, of course, you're going to use this part as the part that we're going to annihilate your vectors. And you develop a highest weight theory with respect to this decomposition, which we call highest L weight, where the L comes from the word loops, since weights are coming from the loop over the Cartan part. Right? And then that's the next theorem, which was also due to Charin-Presley, that the classification of simple modules for the quantum affine algebras is given in terms of highest L weights, which are also called Drinfeld polynomials. So these Drinfeld polynomials are encoding in terms of some generating functions, the eigenvalues of the action of that abelian subalgebra of the quantum algebra. All right, so I'm going to use this notation. So the Drinfeld polynomial is actually not one polynomial, but it's a tuple of polynomials, a collection of polynomials indexed by the nodes of the Jenkins diagram of the underlying finite dimensional Lie algebra. So this I is the set of nodes of the Jenkins diagram of the finite dimensional algebra here, and then I'm going to note by this symbol VQ omega. So for any Drinfeld polynomial, VQ omega, this is going to be the notation for the corresponding simple module here. All right, so how does the story go in the SL2 case, which is the only case that behaves as in the classical situation? So there so for type A, we have evaluation quantum analogs of evaluations, and what is the Drinfeld polynomial of an evaluation module? It turns out that it has this form. So if you start with simple module with highest weight R for SL2, for quantum SL2, then you perform the evaluation procedure and you calculate the Drinfeld polynomial. What you're going to get is a polynomial of degree R. So all of these polynomials have constant term 1. Okay, the Drinfeld polynomials, they have constant term 1. So you get a polynomial of degree R, which is the highest weight, the classical highest weight of the story. And the roots of these polynomials are organized in what's called a Q string, meaning if you find a root of this polynomial, the other possible roots is you obtain by multiplying the one that you found by either Q squared of Q to the minus 2, and you go as far as you can in one direction and the other, and you collect this forms this Q string. Okay? So this is what is written there. So I'm going to use this notation here for these polynomials that have this structure here. Okay? So then it's a very easy combinatorial thing to see that for any polynomial in one variable with constant term 1, you can write it in a unique manner as a product of polynomials of this form in such a way that the strings, no two strings of these can be used to form an even bigger string containing properly both of them. So this is what this condition here is, that you choose a factorization so that you find a root, you go maximum, then you divide by that, and then you do it again and again, and then you get this factorization of the polynomial, which is called the Q factorization. So, okay. So then it's a theorem of Charin-Presley that for SL2 the things go as in the classical situation. If you perform the Q factorization of the polynomial, of the Drinfeld polynomial, it's just one polynomial for SL2. Then the simple module associated to that Drinfeld polynomial is exactly the tensor product of the simple modules associated with these Q factors, which are the evaluation modules, and therefore the answer to the question is the same. The simple modules, which are prime, are exactly the evaluation ones. Okay? So now, how do we go higher rank? So this theorem is false for higher rank, even for SL3. Okay? It's not true that even for SL3 that a simple module is a tensor product of evaluation modules. And for other types, the notion of that there is no quantum analog of evaluation module, so it's even worse. Okay? So, but still, let's use this notion of Q factorization to try to address our question for higher rank. So let me put some more notation here. So let's see, G has this Cartan matrix, and it's a symmetrizable Cartan matrix. You can choose these relatively prime integers that I'm calling di here, so that when you multiply the Cartan matrix by the diagonal matrix containing them, this becomes symmetric. And then I'm going to use this di here to define, so you have your quantum parameter, which I'm assuming is not a root of unit here, okay? So you define this Q index I is just the dith power of Q. And then this, I'm using this notation for the Drinfeld loop-like generators of the quantum affine algebra. And one thing that we use a lot here is arguments using diagram subalgebra. So whenever you have a subset of the Dynkin diagram, of the nodes of the Dynkin diagram, you can consider the subalgebra of the quantum affine algebra generated only by the generators whose indices run over this subset here. So this is also a quantum affine algebra, but it may have a different quantum parameter. So the quantum parameter, so it is the Drinfeld-Gibbon quantum group associated to the loop algebra associated to the corresponding generators running J only over J, but the quantum parameter may not be Q, but it's Q to the minimum of the GIs that belong to these subdiagrams. Okay? So what we do, if we have now a tuple of polynomials, we have a Drinfeld polynomial which is actually have more entries than just one in the SL2, we perform the Q factorization in each entry, but not the Q factorization, but rather the QI factorization of each entry. So you have a polynomial in each entry, you just perform the thing we said in the previous slide for SL2, but with parameter QI corresponding to that entry. Okay? So these are the things that I call Q factors, right? So the Q factorization is the unique way of right. So now you have the node of the diagram that you are in, but other than that is exactly what was in the SL2 case. And So the set, the mood set with multiplicity, so each Q factor may appear with multiplicity. So this is what we call the set of Q factors of the Dirichlet polynomial, okay? All right. So in particular, these modules that have a unique Q factor are very important. They are called the Kirilov-Rchiki modules. So they are so named because in a paper by Kirilov and Rchiki related to mathematical physics, they conjectured that there should exist some modules whose characters satisfied some fermionic formulas, and after a while, it was understood that in the setting of quantum affine algebras, these modules should be the ones whose Dirichlet polynomials are exactly these, which is the ones that have only one Q factor, okay? So the important thing here of this, the definition of the notion of Q factorization graphs is what I'm putting here at the end of this slide, is when you study the reducibility or irreducibility of the tensor product of two Kirilov-Rchiki modules, right? So it's known for a while that there exists a finite set of positive integers, so that this tensor product is reducible if and only if the centers of the string, so these numbers that are, which were the evaluation parameters in the SL2 case, are called the centers of this Q string. So the centers of the Q strings must be related by something like this, where this M in absolute value must be in this set, okay? So in the order that I wrote here, if the M is negative, then this tensor product is highest weight module. If it is not negative, it's not highest weight module, right? So this is important here too. All right, so what's the definition? So we're going to define the notion, abstract notion of what is a Q factorization graph to capture the Q factorization of this Dirichlet polynomial. So to begin with, it's a directed graph. So you have vertices and you have arrows, okay? And then we're going to consider three kinds of decoration of the graph. So the first one is what we call a coloring. So to each node, each vertex of the graph, we're going to associate the node of the Jenkins diagram of G. So this is called coloring, and then we do this kind of picture to remember which color the vertex is painted. And then there is a weight map, which is just the degree of the polynomial that is going to sit there. So this is a positive integer, okay? And then we have a sort of weight map. In the picture, I'm going to mark the weights like that, close to the color. And then we have a sort of weight map, but for arrows, which I call the exponent map, because these are going to keep track of the exponents of the powers of Q that appeared in the previous slide, how the centers related to each other. And then this data has to satisfy some certain conditions. So as I said, so this is actually coming from the fact that here you're going to have a Q string with some center. Here you're going to have a Q string with another center. And the centers are going to be connected in such a way that to obtain one from the other. So if you want the center from here, starting from the one from here, you just multiply by Q to the M2. Okay? So as you move along here, you're telling how you obtain the center of all the other vertices beginning from one of them. So of course, if you complete a cycle like this, you have to end at the same place. So one condition is that M2 plus M3 has to be equal M4, for instance, right? Okay, so these numbers are keeping track of that thing. So in particular, these numbers have to be a number on this finite set that control the reducibility or irreducibility of the tensor product of Kirilov-Rchiki modules. But we want something that really is Q factorization, so we cannot have the numbers inside the set. Part of these numbers have to do with if they have the same color, right? If the colors here are the same, if you are taking tensor product Kirilov-Rchiki modules associated to the same node of the Jenkins diagram, part of the numbers in this set are related to this thing, this fact that the strings may be overlapping. Okay, so you remove those. Okay, so the numbers actually have to be outside the ones that are related to overlapping, not overlapping, properly going out, right? They can be contained, but right? So you remove those if the colors are the same. So I'm going to use this notation here with the tilde for this set with you remove the thing.
I'm sorry. So in the previous slide, you already
is not reducible. So you only mark the thing, because it's reducible almost all the time, right? So if you just pick random number, there is a finite set where it's not, not simple.
Confusing. So here it says that it is reducible if this integer is in that set.
Exactly. There is a finite set where it is reducible.
But we're requiring these epsilons to be in that set.
Exactly. So I'm marking when it is reducible.
Oh, okay.
Right? So when it's not marked, if you see a graph, for instance, like this, and you want to study the tensor product of Kirilov, Rchiki associated with this is simple. Okay? So this is reducible, but that one is simple. Okay? All right. All right, so then, given that the infinite polynomials, now should be sort of obvious how to associate a graph with these decorations, right? So the set of vertices is just the multi-set of Q factors. So if a factor appears with multiplicity, you put as many vertices in the graph. And the coloring is, of course, going to be the node from where it came from. The weight is just the degree of the polynomial. And there will be an arrow, so Raimundo just explained to us how there will be an arrow. Right? There will be an arrow if the corresponding tensor product of the Kirilov-Rchiki modules is reducible, but it's an arrow, so you have to keep track of the order. So the arrow is pointing out such that if you do the tensor product in this order, the module is highest weight if the number is positive. Right? Okay? So you put a bigger thing in front in order for it to be highest weight. Okay? If you do the other order, it's also reducible but not highest weight. Okay? All right, so, and then the number that you put, that you decorate the arrow with is exactly this M. Okay, so here are some examples. For instance, for type A2, the only Q factorization graph is a singleton. But you can use the notion of what we call a pseudo Q factorization graph, which is you don't remove, you just, I should have put some, where is it? No, it's here. Yeah. If you don't remove this, if you allow to use the numbers from here as well, if you allow to use the numbers from here as well, this is what we call the pseudo Q factorization graph. So you can do that to study things as well. And for instance, this one for SL2, what is it representing? It's representing that Dirichlet polynomial there. So the degree is 1 in each one of them. But this is, the number 2 is exactly the number that you form a string. You have a string with one node, another string with one node that are differed by Q squared. So you make the actual Q factorization graph is just this. Okay? So for SL3, for instance, if you take a node 1, node 2, both with degree of polynomials of degree 1, there is just one number in the set. So the only kind of Q factorization graph that you can do is this, which is representing this Dirichlet polynomial, or this. And this has to do with duality. So if you invert arrows, it means that you consider the dual modules of this kind of things. So if you raise the degrees of the polynomials instead of 1, 1, then these sets become larger and larger. There are more and more numbers there. So for instance, you can form here Q factorization graph for any number between using either 4 or 6. So this is going to be representing that Dirichlet polynomial. So here is an example with repetition of color. So I'm using the middle node. So this is type A3. It has 3. The Deakin diagram has 3 nodes. I'm looking at the middle one for both. So I'm using Dirichlet polynomial supported at the same node. So the 2 is the same 2 that is there. So this is not allowed if you want a Q factorization because you have strings that can be joined to form a larger string, right? So if you really want a Q factorization graph, you can only use the 4. Okay? And then you can form, by the way, so this is sort of, so this kind of thing here, as well as there, this is a shadow of this very general Hopf algebra thing that you have the trivial module sitting as a submodule of the tensor product of a module in this dual. So in fact, the module here is the dual of the module here. The module here is the dual of the module there. So that's why you have the reducibility, for instance. Okay. All right, so you can form more interesting things like this or like that. So how we are going to use this kind of machinery to try to answer the question that was in the first slide? How do I use the notion of Q factorization in order to try to understand which simple modules are prime or not prime? Okay, so a couple of observations here is that, so in this category, the order of the tensor product is important. So the things are not, the tensor product in the opposite order is not isomorphic to the original order. But if they are isomorphic, then the tensor product is simple. Okay, so if you have two simple modules which tensored in both orders give isomorphic modules, then the thing is simple. And another one is an early result of Chad and Presley that if your tensor product is simple, then how are the Q factors of the product of the two Drinfeld polynomials are related to the Q factors of each one of them. So it's going to be simple. If it is simple, then the Q factors of the product is exactly the union, counted with multiplicities, of the Q factors of each of the tensor factors of the module. So this is what I'm going to use this terminology here called dissociated Q factorization. So if this happens, if the multiset of Q factors of the product is the union of the multiset of Q factors of the two given original polynomials, I'm going to say that the omega and pi have dissociated Q factorizations. And that's exactly what happens when the tensor product is simple. Okay? So an immediate consequence of this is that Kirilov Rchiki modules are prime. Because there is only one Q factor. If you break this into a product like this, well, they do not have dissociated factorization by definition because you're having strings that you broke the string. So of course they can be joined to make a larger string, right? So this is the first example of a tree that is prime, for instance. The Kirilov Rchiki module is only one vertex, so it's a tree. So this gives a rough method to try to answer the question. So given a Drinfeld polynomial, you compute the set of Q factors. So the reason for the quotation marks there is because this part is difficult, right? Finding roots of a polynomial is difficult. So suppose you are able to find the roots of polynomial, then you can perform the combinatorial thing of arranging everything in strings, and you find the multiset of Q factors. All right. And then you can partition this multiset of Q factors and then form the Drinfeld polynomials that are just the product of the ones that you put in the first side and the product of the things you put on the other side. And remember, things can have multiplicity, so you can put different, the same Q factor in both things because it's a multiset, right? So if it has multiplicity, you can split the copies from one side to the other as well. And then you figure out, you have to study all these many tensor products, figure out if they are simple or not simple. And it follows from this proposition that, the module is going to be prime if and only if all of these tensor products, for all possible decompositions, they are reducible. Right? Because if you find one partition that is simple, then end of story. You decompose your module as a tensor product of two simple modules. Okay? Right. So, for instance, this gives the answer for Drinfeld polynomials with exactly two Q factors. This thing is going to be prime if and only if the centers are related by the numbers that were in these sets that we use to define the Q factorization graph. Right? So next step is tree vertex. Right? And we're going to get there. So tree vertex is the only theorem that was not in the title of the talk. Now, one thing that we prove very early on, and then at the end I'm going to mention from where what is the thing that can be used to prove, is that if the module is prime, then the Q factorization graph is connected. The converse is certainly not true. I mean, there are many, most of the connected graphs are not going to be prime, right? But this reduces, so in this part here in particular, we can restrict our attention to partitions in such a way that the Q factorization graph of each factor here is connected as well. Okay, so you have to look at connected things only. Okay? All right. So let's go to the first theorem, which was the second line of the title of the talk. So remember, we cannot have oriented cycles. We can have cycles, but we cannot have oriented cycles because this means that the power of Q, so this is moving powers of Q of the centers. You came back to the same place, so it should be Q to the 0, but these numbers are all positive, so we cannot have oriented cycles, right? You can have cycles, but not oriented cycles. And whenever you have a graph, a directed graph with no oriented cycles, then the set of arrows induces a partial order on the set of vertices. Right? Because an arrow, after all, is actually a minus, is a relation order disguised, right? So you just look at that. So this is, so you just pick the transitive extension of the relation, saying that the head of the arrow is smaller than the tail of the arrow, and you have a partial order on the vertex. And what's a tree? So a tree is a graph with no cycles. So there are no oriented cycles, but there could be a cycle. Okay, so a tree is a graph with no cycles. And so I want to talk in this first result is about totally ordered graph. So what's a totally ordered graph? Is a graph for which the set of vertices, the partial order is actually a total order, right? So the only kind of trees which are also totally ordered must have just one branch. If you just draw something which is a tree, has no cycles, you're going to see that if it is a tree and it is totally ordered, it has to be aligned like that. Right? So one result that we proved early on this thing is that for every type, if your Q factorization graph is a totally ordered tree, meaning it's aligned, then the module is prime. Okay? This just has a simple proof, but I don't think I'll have time to get there. If I have, I'll show you as well. But then for type A, so this is actually, it's the first of the main theorems I'm presenting, but it's actually the last to be proved. For type A, we proved a much stronger generalization of this, that in fact, every totally ordered Q factorization graph is prime. Okay, so for instance, a Q factorization graph ordered by a triangle is prime, because it's any triangle, since you don't have oriented cycles, any triangle is totally ordered, right? Here is the maximal element, here is the minimal element, and this is certainly in between. Okay? And there are plenty of these. So this is one of the results. And do I make a comment? No, I don't make a comment of this. So the reason this is proved for type A only is that for doing while the first one here, we can do most of the proof dealing with combinatorics and some more general things. Here we have to check some conditions which we use precisely what numbers are in these sets here. So the method of the proof in principle works for every type, but then you have to check things that are related with the set, and then it becomes a case-by-case analysis. So that's the reason. So in particular, this theorem recovers most of the primality results we had BCC. Okay? So BC is before COVID, but BCC is before connection with cluster algebras. So before David Hernandez and Bernard Leclerc came with this amazing paper relating this representation theory with cluster algebras, there were some prime modules which were known, and most of them, in the end, if you compute their Q factorization graph, they are totally ordered. Okay, so for instance, minimal affinizations that I gave several talks about, they are actually covered by the first one. Every minimal affinization is a totally ordered line like that. But then later on, Evgeny Mukhin and Charles Young they defined this notion of a snake module. And it turns out that the snake modules also have Q factorization graphs, which are totally ordered, not lines, but totally ordered. And so the version of this talk I gave in Chengdu, after the talk, Alexander Molev came to ask me, so what about these modules that I studied, called these Q modules? At the time they were studying these, even though the notion was around already, people were not thinking about this question at that time for some reason. So the question was simply not addressed in the paper. But it turns out that their modules also fall in this kind of thing. So totally ordered Q factorization graph. The Q factorization graph of those modules are totally ordered as well. So they are prime if they are connected, because the graph may not be connected. But every connected component of the graph of these Q modules are totally ordered. So you have several prime modules there. Okay? So let me just show you. So for instance, this is a Q factorization graph of a snake module. Okay? Of course, the definition of snake is related to this notion of Q factorization here, but the reason it's called snake is not transparent here at all, but I'm not going to go there. But this other one, which looks, it's the same directed graph, it's only the decoration that is changing, is the Q factorization graph of one of these Q modules, and it is not a snake module. So the first one is a snake module. The second one is a skew module, but not a snake module. So, okay. So the decoration is important here. It's not just the graph. It's not the set of errors. Okay. So let's go to the only theorem that was not in the title of the talk, which is, so we know what is the answer for primality of simple module with exactly 2 Q factors, or what about 3? What about if the Q factorization graph has 3 vertices? Well, for 3 vertices, there aren't many options, right? We can have a graph like this, which is a direct line, therefore it's prime. We can have something like this, which is totally ordered. So at least for type A, we know it's prime. Or we can have something like this, or the arrows like that, right? The opposite direction is always related to some dual model of that, right? So, in order to give you the answer for type A, characterization of which graphs of this sort are associated to prime simple modules, so let me introduce a little bit more of notation. So, by the interval, so if I have 2 nodes of the Dinkin diagram of G, it's well defined what means the interval between them, right? So everything you take the 2 nodes and everything in between. It's well defined what is in between for Dinkin diagrams, right? Okay. And then suppose that you choose a subdiagram that contains the whole interval between these 2 nodes, and then I'm going to define a subset of the set of the sets that we are using here associated to the diagram J. So what is that? So you go to the diagram Sub Algebra. So you take your Drinfeld polynomial and forget everything that's outside J. So this becomes a Drinfeld polynomial for the diagram Sub Algebra, and you pose the same question. You study tensor product of Kirilov Rchiki modules there, and you form a set. So if you have inclusion of subdiagrams, these sets are included as well. So you have a chain of inclusions here, right? So for non-simply laced case, this definition has to be written a little bit more careful than this, but since we're going to talk about type A only, this definition is correct as written here. So suppose you have a type A algebra, and you have a tree with 3 vertices, which does not contain a cycle. So it's one of these 2 things. So you have a characterization of when this tree is prime and when it's not. So what we're going to do to express the answer, so let's call it Ij, the subdiagram. So you fix 2 nodes here, so the middle one and one of the 2 extremal nodes here, that's extremal vertices here. And you consider in the Dinkin diagram the whole interval between I and I1 or between I and I2. Okay? And then you call it Ij, the minimal connected subdiagram of the Dinkin diagram, for which contains the whole interval, and it's sufficient to produce the number m, which is decorating the m. Okay, as I said, these sets are contained. If you make the diagram J bigger, the new set becomes bigger. It contains the smaller one, right? So the number m is going to be, if you choose J is equal I, but maybe you could choose a smaller diagram and the number m would already be there, okay? So choose the minimal thing. So this is what the ij is, okay? And I'm going to choose this notation. So whenever I choose J, either 1 or 2, I'm going to denote by J prime the other one. So if J is 1, J prime is 2, and vice versa, okay? So this graph is prime, meaning the underlying simple module is prime if and only if, for one choice of either I1 or I2, the other one is going to be in this minimal set related to the J you fixed here. The number for the other one, so if I chose J equal 1 here, I'm now looking at I2 and M2. It also has to be in the same, be produced using the same subdiagram. And then there is a condition that is uglier, but it's also sort of natural if you study what is happening with duality here. So let's not say too many words, but you see here I'm using the longest element of the Weil group associated to this Jenkins subdiagram here, for instance. So all of the conditions that are here so far are very natural. Actually, in less than a page, we prove that they must be there. And then we spend 15 pages proving that if all of these conditions in the first line are satisfied, your module is going to be prime if and only if this third one, this fourth one, is satisfied. So this is precisely the classification of prime trees with 3 vertices for type A. Okay? So our goal was to characterize, for at least for type A, the primality of any tree. So this is sort of the first step. Okay? Now, why are trees prime? Oh, sorry, the first line of the title. Why are trees real, right? What's written here. So one of important things that we use is a corollary of this theorem, which is this one. So this graph is not prime. So this is it's a graph as here, right? It's a particular case of this where it's completely symmetrical. So the colors on the extremes are equal and the weights are equal on the extremes and the arrows are decorated by the same thing. So that's the particular case. It's completely symmetric. Okay? So in this case, if you just put this data in these conditions here, you're going to see that it's not satisfied. At least one of them is not satisfied. I don't remember which. And therefore, it's not prime. No, sorry. No, my statement, it's not prime. So all of these conditions are satisfied. Sorry. Yeah, so you just check that if you put this completely symmetric thing, all the conditions are satisfied, and that therefore this graph is not prime. Okay? So this means that, in other words, in terms of tensor products, if you go back to representation theoretic statements, it just means that this tensor product here is simple. Okay? So I already told you or recalled what it means to be a tree, so what it means to be real. So to be real, it means that if you take a simple module and tensor it with itself, it's still simple. And this definition arose exactly from the connection with cluster algebra. So there is all this machinery to study which modules are prime or not prime using the theory of cluster algebras. And so motivated by this, Hernandez and Leclerc defined this notion of what it means for a module to be real, and it means the tensor square is simple. Okay? So the last theorem, which was the first line of the title of the talk, is that for type A, every tree is real, and the only reason this one is for type A is because we use this corollary. All the rest of the proof is written for, it works for, there is no type mentioning in the rest of the proof here. So it's expected, maybe if one uses different techniques than we used here, you can deduce this in a simpler manner, this particular case. So this particular case up here, maybe it's deducible for all other types in a simpler manner than what we did, because we were actually aiming at something else, and then this came about. Okay, so what about the proof? So maybe I'm going to show why trees are real after all. So, but let me make some general remarks about this. So the actual work is to prove several criteria for a two-fold tensor product of simple modules to be highest weight. So this is the main job of the whole procedure, to establish several criteria. And then, the things we used for proving these are not new. So they were around, we just worked with them and proved this criteria. So what is the role of graphs here? So the role of graphs is, it's an efficient manner for you to keep track of the combinatorics involved and then express the results in an understandable way, which is not a list of 300 things. And so you can keep track of what you are doing. Okay? So you are able to do that. And, well, I already mentioned this. The reason that the results for type A are for type A is that the proof, the way it is built, we need to check if some numbers are or are not inside here to see if they satisfy the criteria that we established or not. And in principle, everything can be done for all types, but you have to check using the correct sets of numbers, right? All right, so let me put some fundamental facts up which are used in the proof. So the first one, which is very old result, it's around for a very long time, is that a module, a finite dimensional module for the quantum of analogy is simple if and only if both itself and its dual model are highest weight modules. Okay? And this has a consequence that if you want to apply this for tensor products, so I want to study if a tensor product of two simple modules is simple or not, then what I have to do is to study the tensor product in both orders, and instead of proving it's simple, I prove that it's highest weight in both orders. So, okay, so this working with duality, you have this. So this is around for a long time. So this is one thing. And why the criteria are all two-fold tensor products? I could have to study bigger tensor products with many factors, but this is a result of Davi published in 2019. So I was already working on this kind of things, and every time I wanted to use this kind of result here. So what is the result? If you have a tensor product with many factors, and you want to conclude that it is highest weight, it suffices to study every ordered tensor product, two-fold tensor product you can extract from this m-fold tensor product. So you study them all. If all of them are highest weight, then the original one, the big one, is also highest weight. Okay? So I can then establish a criteria for two-fold tensor product and use for all pairs and conclude the big one is also highest weight. Okay? So the reason we put the name here is that the important and complicated part here is this direction that I said. If you test 2 by 2 and then you conclude the big one is, but the converse is true as well. This was not written in Davi's. We just put a proof here for having a proof. So the way you're going to use that we mostly use this is the following corollary. So we want to study a tensor product like this. So suppose you find any factorization of your two Dirichlet polynomials such that you have the following properties. So if you look at the factors of one of them, so you have pi and you have pi tilde. If you look at only for pi, ordered, then it's highest weight, all of them. Same thing for pi tilde. So this is always possible. If you take the factorization is exactly the key factorization, so you have a partial order, you can choose any linear extension of this partial order, this is going to work. However, we want more, and then the key factorization may not work. Because you want that if for all of the factors that you cooked up here and all of the factors that you cooked up here, the ordered tensor product here is also highest weight. Okay? So this is a corollary, easy corollary from this Davi's theorem. And with this, I can finally prove that trees are real. So let me sketch here. So what's the important thing about trees is that they have boundaries, and if you remove boundaries, they remain a tree, connected tree. So you have a tree, so let's say that you have a, let's put like this. So suppose this is a boundary node. What is a boundary node? It's a boundary whose valence is a vertex whose valence is at most 1. So since it's connected, I'm assuming things are connected, it means that the valence is exactly 1. Okay? So it's connected with only one other vertex. Right? So this belongs to the boundary of your graph. So it's connected to only one, and without loss of generality, I'm going to suppose the arrow is like this. So if it's not like this, you just dualize everything on I'm going to say. So this one may have many arrows or not coming out in whatever is going to happen here. There is a big thing here. Okay, and I'm going to look at this cut of the graph. Okay? All right. So since this has no arrow to anything else, only to this, and this is bigger than this corollary is telling us that I'm going to be lazy here. Instead of writing VQ of omega, I'm going to write just omega. Okay? So this, by definition of what arrows means, this tensor product is highest weight. Okay? Just by definition of what the arrows mean. Okay. So let's call the product of all the factors that are here, let's call it pi. Like this, var pi. Okay? So notice that if I remove that thing, I got this graph. This is a tree. This is a tree as well, with one vertex less. So I can use induction hypothesis here. Okay? Remember, the first step of induction is proved because first step of induction means you have only one vertex. This is a Kirilov Rchiki module, which we already know is prime, is real, sorry. Okay? All right, so I can use induction hypothesis to this graph here. Fine. So let's write the things like this. So my original graph pi, so this is the whole product here. So that pi with this omega is my original Dirichlet polynomial. So I'm going to write this as this times omega. But I'm going to further split this. So I'm going to write this as pi prime, omega prime, this omega prime here, times omega, right? So this is whatever else happens here when you divide by this. Okay?
But now this omega prime might not be connected.
To what?
This omega prime is not necessarily is a connected tree.
It may not be a connected tree. Yeah. So I have no idea if this omega prime is a boundary node or not. It doesn't matter. Okay? All right, so in particular, note that, so this is going to be important in a few moments. I can write pi squared. So what do I have to prove here? I forgot to. So because of the criteria here, all that I need to do is to prove that pi tensor pi, VQ pi tensor VQ pi, is highest weight. This is what you have to do for proving, because in order to prove that something is simple, the thing that's written up there, what I have to do is to prove that the tensor product in both directions is highest weight, but this is symmetrical, so that's all I have to do here. All right. So this pi squared will be written like this. So one time I write just pi, and the other time I write just like this, right? I just divide them. Okay, we are going to use this in a moment. So now, let's look at these three tensor products here. Pi with omega, pi with var pi, and omega with var pi. So since this, so what is pi? Pi is this whole thing here. This is bigger, and this is not connected to anything else. So the corollary here is telling me that this is highest weight by construction. Okay, so I just take the decomposition, the factorization I take. This has just one factor. I use this on the pi side there. And the pi tilde side there, I just use the Q factorization, and it satisfies the hypothesis, and fine. Okay. Now, this one, I'm going to further write it like this. So I'm going to decompose this again. So this is omega, tensor var pi, tensor y pi. Right? And now I have a threefold tensor product, and I want to deduce if this threefold tensor product is highest weight or not. If it is highest weight, then it projects on that one, and therefore this is highest weight as well. Now I will use this criterion of checking 2 by 2. Now, this is the same as that. And this is the same again. So this is highest weight. So I just need to check that this is highest weight here. But this is by induction hypothesis. Okay, so this is highest weight. So now, look at what is written here. If you look at pi, tensor omega, tensor pi, if you prove that this, what is the product here? This is exactly pi squared. If I prove that this is highest weight, then this is going to project into pi, and therefore that's going to be highest weight. So by David's criterion, if I prove that this one is highest weight, I'm done, because then all two-fold tensor products were checked to be highest weight. So I just need to prove this. So how is this looking like? So that is the difficult part. So I'm going to further write var pi in the following way. So I'm going to split, so I'm changing the decomposition here in the corollary every time and choosing smarter decompositions. So I'm going to write this as something that I'm going to tell you what it is. And there is the omega prime, and whatever comes out. So I have to define this, and this is whatever is not there, right? So pi has omega, sorry, I wrote it. Why did I write? Pi does not have this. Why did I write this here? No, because this is not this pi, it's this pi. Okay. So what is this? So you look here, whatever is coming towards omega prime, and you collect the connected components that Raymond said, of the things that start with an arrow, so it's bigger here. This is bigger, fine, but this is smaller, then you don't put. So omega plus, pi plus, is the product of everything on these branches that start with an arrow that goes to a bigger thing. Okay? And omega minus whatever else you can multiply on the other things. Okay? So again, we're going to look here and start this tensor product, right? We're going to put tensor everywhere here. Now, using David's criterion, I have to study every two-fold tensor ordered two-fold tensor products that I have here. And all of them, except one, I have already dealt with. The only one that I didn't deal with, I mean, the way this omega minus is constructed is such a way that, for instance, if you want to look at the tensor product omega plus with omega minus, these are things that are not connected. Okay, so it's highest weight by the corollary. Okay, and the other things I had details, so the only thing that I really have to work is the tensor product of this with this. But what is this? So this is, yeah. So what is the Q factorization graph of a Dirichlet polynomial, which is omega squared, omega prime? So you have omega, omega prime. And now you have another omega, and there is no error here. So this is exactly the corollary up there. It's not prime, so this is highest weight. So that's where the corollary is. And this is so okay, I think I'm already gone over time, so let's stop here. Thank you very much.
Questions? Comment?
Sorry? No, not necessarily. So around the same time, I don't remember if it was before or after he and Leclerc put out the first paper with cluster algebra, connection with cluster algebra. David put out this, where is it? No, it's after. David put out a paper proving a theorem similar to this, but instead of being concerned with highest weight, is concerned about being simple. So this was already motivated by the cluster algebra connection. So this first theorem is the same statement, just change the word highest weight by simple. So this is all behind this connection with cluster algebras. And then after a while, I was already looking at these kind of things, and I asked David, so is it true if I change simple to highest weight? And I don't know, less than a year later, he came with this answer. Now, if you put simple here, the converse is trivial. There is nothing. If you put highest weight, the converse is not trivial, but it's not difficult. So the important part is the part that David. So this proof here, how did David prove this? So he uses all this machinery of Q characters and I believe a little bit of R matrices as well here. I don't remember if R matrix enters here or not. But this uses this machinery. And then the theorem about simple ones, I mean this direction, because the other was trivial for, is a consequence of this. So that one can be recovered from this one now. Yeah. It is, I mean, yeah, the techniques are sort of morally the same, but I won't be able to tell you what the precise differences are. But yeah, it's some deep machinery of dealing with Q characters, and that David is the best expert for all this.
Are there any more questions? All right, so let's thank Adriano again.
Thank you.